Hi everyone, it's Miss Mantle. Today we are going to be simplifying higher ordered roots. So last time we talked about simplifying and dealing with square roots, but we were just focusing on the number values. Today on our opener, we're going to see some square roots with some variable answers, and I'm asking you to do some matching. So I'm hoping that that will help you, even if you're not really sure what to do. So go ahead and take a few minutes to work with your table group to match the following expressions. And then, whoopsie, and then when you're done, go ahead and fill in the perfect cubes below. If you need to grab a calculator, you certainly can. Alrighty, here we go. So number one, the square root of 121 I know is 11. And so, uh, and I, even if I don't know what the square root of x squared is, I'm looking for 11 over here. And so E is going to be my match. And I'm going to cross them out as I go. Now the square root of 32 is 16 times 2. And even if I don't know what to do with the x to the 4, I do know that this is going to become 4 root 2, just like numerically. So I'm looking down the column here and I notice that there's a 4 root 2 with number C or letter C. Okay, so if I continue in the same fashion, number 3 is G, number 4 is I, number 5 is B, number 6 is F, number 7 is D, number 8 is A, and number 9 is H. So this is what we're going to be focusing on today, is how to simplify when we have variables underneath the square root. Okay, so if we look up here, for example, with number 1, we know that the square root of 121 is 11, but we also then have the square root of x squared. Well, the square and the square root are opposite or inverse functions, and so they kind of cancel each other out. All right, but we're going to talk a little bit about why there's an absolute value around there in our notes today. So even if I didn't know exactly why it was an absolute value of x, I can still sort of deduce from this why it is an absolute value, or why this is the answer rather. Number 4, the square root of 49 is 7. The square root of x of x squared would be x. The square root of y squared would be y. And similarly, I might not know exactly why there's an absolute value around the x and y, but I can deduce that my answer there would be I. Okay, so maybe like if we look at number 9. So for number 9, if I just look at the number parts, I've got 45 over 5, which is 9, and the square root of 9 is 3. And then if I look at the x parts, I've got x cubed over x. And if I simplify inside there, I'm going to end up with the square root of x squared, which is x. So far I've got 3x on the top. And then if I look at the y terms, I've got y squared over y to the 4. Okay, well, I've got 2 y's on the top and 4 y's on the bottom. And so that really means that I have root y squared on the bottom. And so I'm going to end up with 3xy. Again, I might not know exactly why there's absolute values around there, but I can deduce that my answer here would be H. Okay, so this is what we're going to be looking at and focusing on today, is both numerical and variable terms. And we're going to be sort of ramping it up because we're going to be looking at higher roots. So in order to talk about higher roots, we should probably look at some perfect cubes. So some of these I expect that you should know, but then, some of them maybe you're not quite as fresh. All right, so a perfect cube just means that you're multiplying a number or a variable even by itself 3 times. So 2 times 2 times 2 means 2 to the third, which is 8. 3 times 3 times 3, 27. 4 times 4 times 4, 64. 125. So you should start getting used to these perfect cubes. I know probably you are not quite as adept as with square roots, but that's why we're practicing. This is 216, 7 cubed is 343, 8 cubed is 512, 9 cubed is 729, and 10 cubed is 1,000. Now, what's unique about cubes is that if I take a negative number and cube it, I get a -8. So as opposed to like a square, right? If I take 2 times 2, that's 4. If I take -2 times -2, that's also 4. So it doesn't matter if my number that I'm squaring is positive or negative, my answer is always going to be positive. But that's not true for cubes. And so we have to be careful when we're taking the cube root to take into consideration any root, a cube root that is negative. And that's the same for um, any odd powered root. All right. So we're going to talk about radical expressions today. Let's review. In the expression, the square root of a squared, the radicand, a squared, is a perfect square. If a is 5, then we have 5 squared, which is root 25, which is equal to 5. And if a is -5, then our result will also be positive 5. So the symbol root a squared does not represent a negative number. It always represents the principal square root, which is positive. So technically, whenever you take the square root of a number, if it comes out, I should really put it out. I should really put it in absolute values because I'm not sure if the number originally is positive or negative. But for our purposes, we're going to go ahead and just say assume all variables are positive, so we don't have to worry about that absolute value symbol. But when you get into pre-calculus or even calculus, you might have to consider when you have an absolute value. Okay, so just like we looked at perfect squares of numerical values, we can look at perfect squares and square roots of variable expressions. So if I have the number 36, well, that's written as 6 times 6, which is 6 squared. And if I write it as a root, I can say the square root of 36 means the square root of 6 squared, which is 6. So we're going to focus on the root part today. But it's important to understand sort of what's happening when we break down, it down. So if I have x squared, which is a perfect square, I can go over here and just say, well, the square root of x squared is x. Technically, it's the absolute value of x, but we're going to just say that it's x for our purposes. If I write it as a square, that means that I had x times x, which was x squared. And remember that the power that's written here that is not actually not written but implied is a 1. So that when I multiply my x terms together, I'm adding the exponents together. Okay, so that leads us to some higher powers. If I have x to the 6, I need to have 2 x's so that I have a perfect square. And the way I'm going to break down x to the 6, I need to have the same term such that I'm adding 2 numbers that add to 6 that are the same number. And so that's going to be 3 and 3. So x to the 3rd squared. Why is that x to the 6th? Well, because we have another property called the power of a power property. X to the 3rd to the 2nd, I multiply those together and get x to the 6th. So that means when I take the square root of x to the 6th, it's the same thing as if I say the square root of x cubed squared, and the square and the square root symbol, they are inverse functions. They sort of cancel each other out there. And I would say that the square root of x to the 6th is x cubed. It is not a coincidence that it's half. So using that same idea for x to the 10, if I have 2 x's multiplying together to get x to the 10 written as a square, that means something quantity squared. I need 2 numbers that are the same that add to 10. That would be 5 and 5. So x to the 5th would be how I would write this as a square. And so then the square root of x to the 10 means the square root of x to the fifth quantity squared. And just like before, we can cancel these two operations and call this x to the fifth. Again, it's no coincidence that we're dividing by 2. 10 divided by 2 is 5, 6 divided by 2 is 3. Okay, so then let's talk about cubes. We looked earlier at the perfect cube 8, which was 2 times 2 times 2. That means the cube root of 8 is equal to 2 because I can write 8 as a perfect cube, 2 cubed. And just like before, the cube root and the cube cancel each other out, and so I would get 2. So similarly for a negative, I can cube root a negative number, which I know feels weird. But if you think about this, I'm multiplying some number 3 times together to get a perfect cube to be negative 27. Well, we know positive 27 is 3 times 3 times 3, but I need my answer to be negative, which means negative 3 times negative 3 times negative 3. So therefore, when we work backwards, the cube root of negative 27 is negative 3. So anytime you have an odd index, an odd root that you're taking, if the thing that's underneath can be negative. With even numbered powers, we're not allowed to have negatives underneath the square roots or the fourth roots. Okay, x cubed means x times x times x cubed. So that means the cube root of x cubed is going to be x. Now, this one would not have an absolute value around it because an absolute value implies that I would have 2 possible values that could go in for x, but with a cubic, that doesn't work, right? Just like we saw above, I've got negative 3 times negative 3 times negative 3, which is negative 3 when I take the cube root. It's only positive 3 when I have the cube root of positive 27. Okay, lastly, I need 3 things multiplying together to get a perfect cube. So this time, x to the 6th, that means I need 3 numbers that are the same that add to 6. And so 2 and 2 and 2, because I can add those exponents together. And so that means that the cube root of x to the 6th, which I can write as x squared to the 3rd, is going to be x squared. Okay. So let's just simplify. Let's do some examples. And it says every real number has exactly, well, this is from before. Every real number has exactly 1 cube root in a system of real numbers. And this is true for all odd powered roots. Okay, so let's go ahead and simplify. So I want to simplify the cube root of 64x cubed. So this is just sort of similar to what we did yesterday with the square roots. So I know that the 64 can be written as 4 cubed, and x cubed is already cubed. So you don't have to write all these steps, but I'm going to go ahead and just write them for a minute so you can see. You can break this apart and evaluate each of the number bits or the pieces separately. And so the cube root of 4 cubed, the cube root and the cube sort of cancel each other out and we're left with 4. And then the cube root of x cubed, the cube root and the power of 3 cube cancel each other out. And so that's just x. And so your answer here would be 4x. Part B. For this one, same idea, except I have a fraction. So I can split this apart into a top and a bottom. Now the negative, I can decide to put it on the top or on the bottom. It doesn't matter. I like to put it on the top personally. And is 216 a perfect cube? If I look back at my list, yes, it is. So the cube root of negative 216 is negative 6 cubed. And the cube root of 125, or the cube is, oops, let me delete there. This is 5 cubed. And so the cube root and the cube and the cube root and the cube are going to reduce, and we're going to end up with negative 6/5. Okay, so we're going to extend this to higher powered expressions with roots and variables. We're going to add and subtract just like we did before, and multiply and divide. And the thing is that you can use all these properties as long as you have like terms. Let's turn the page. All right. So there are also fourth roots and fifth roots and so on. So if I'm looking at the fourth root of a equal to c, that means that c to the fourth is a. And so we're calling these nth roots. All right. I feel like we need to make sure to make a note that, let's do this. Let's say here that you can only have, I'll put a bullet here, can only have positive numbers with even roots. So like the square root of 10 or the fourth root of 60. But you can have positive or negatives under odd roots. So you are allowed to have the cube root of 27. You are allowed to have the fifth root of negative 32. It just means that if you have an odd power with a negative root or negative radicand, then your answer will be negative. Okay, so sorry that wasn't super clear. All right, so let's go ahead and simplify. So it says simplify the following radicals, assume all variables are positive. All right, for this first one, we have the seventh root of 5xy quantity to the seventh. Okay, well, that's the same thing as if I said the seventh root of 5 to the 7, x to the 7, y to the 7. The seventh root and the power of 7 cancel each other out. And so we're just left with 5xy. Nothing too exciting here. Okay, this next one, it's a square root. Let's just practice with the square root for a minute. So 112, let's see, I'm going to use my calculator here and see, is 112 divisible by 4? Yes, it is. Maybe something bigger. I noticed that it's 4 times 28, and I know that 28 has a 4 in it as well. So that must mean that 112 is divisible by 16, which it is. So I'm going to write this as 16 times 7. And then I've got x to the fifth. I don't want x to the fifth. I just want squares because I'm looking for a square root and I want perfect squares. So I can write it as x squared times x squared times x. So I can break it apart into squares. If you want to call that x to the fourth, you can. I'm just going to break it down into the smallest pieces. The same with y to the 9. I can write that as y squared times y squared times y squared times y squared times y. Oh my goodness. Okay, so all the things that are perfect squares, this one, 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 these are all going to come out. Let me do a different color there. All these are going to be I'll do yellow. All these are going to be coming out of the root, all these perfect squares. So the square root of 16 is 4. And then there's going to be stuff left over. So the 7 is left under the root. Now I've got an x squared. When I square root the x squared, I'm going to get x. That's here. And x squared is going to be x. That one's here. And then I've got 1, 2, 3, 4 y's that are going to come out. 1, 2, 3, 4. And everything that's left over, the 7, the x, and the y, are going to be left over under the root. Okay, so let's clean this up. I don't know why I'm using all these stupid colors. Uh, okay, so let's clean this up. Let's say what our final answer is. We're going to have 4x squared, y to the 4, root 7xy. Here's my final answer. Okay, now I know I kind of did it the long way. Maybe we won't have to do the long way every time. You could have done it, let me do it in black over here. So we could have said 16 times 7, x to the 4, x, y to the 8, y. This is going to be 4. This is going to be x squared because I'm square rooting. This is going to be y to the 4 because I'm square rooting. That means I'm dividing my exponent in half. And then I have the 7, the x, and the y that are left over, which is what we ended up with over here. Okay, let's go ahead and go to our next problem. All right, so the cube root of 40x cubed. Well, I know that x cubed is a perfect cube already, but 40 isn't. I'm going to look at my list of perfect cubes, and the smallest one is 8. And I know that 8 is a factor here, 8 times 5, x cubed. Well, you don't have to do this. You don't have to break it apart into 2/3 and then x like this. But just to iterate, like, as long as you know what the cube root of 8 is, the cube root of 8 is 2 cubed. And so then that's going to come out. This is a perfect cube. This is a perfect cube. So anything that's a perfect cube is going to reduce and come out of the cube root, and anything that's left over is just under the root. Okay, so we get 2x cubed root 5. Part D, now we haven't done fourth powers, so let's just kind of investigate for a minute. If I have 2 times 2 times 2, that's 8 times 2 again, that's going to be 16. So 2 to the 4th is 16. If I can write 48 as a factor of 16, then I am very stoked about that. 48 is 16 times 3. And x to the 6th, I'm going to write as x to the 4 times x squared, so that there are 6 x's there. I'm going to show this step writing 16 as 2 to the 4th, and then I'm just going to carry everything else down. And then I want the perfect fourths. Anything that's a perfect fourth is going to pop out of the root. So the fourth root of 2 to the 4th is 2. The fourth root of x to the 4th is x. And then everything that's remaining that isn't a perfect fourth is going to stay under the root. Here is our answer. And we're not messing around with the absolute value thing like we saw in the opener because we're assuming all variables are positive. Okay, let's do a couple more. Okay, let's see here. Let's see. We're doing 81, which is not even, so it can't be divisible by 2. Let's see. 3 times 3 is 9. Oh, and 9 times 9 is 81. So that means that 3 to the 4th is 81. Perfect. So I'm going to have 3 to the 4th times a to the 4, a to the 4. Well, it's already even, so you can just leave it if you want, or you can break it apart. B to the 4, b to the 4, b to the 4, and then I'd have b squared. So 14 divided by 4 doesn't happen, but 8 divided by 4 does. So when you have a power, you have to divide evenly. 8 divided by 4 is 2, but 14 divided by 4 is a decimal. C to the 5, I can write as c to the 4 times c. All right, so I'm looking for all the perfect fourths. Here's one, here's some. These are all perfect fourths. So anything that I didn't circle is going to stay under the root. So the fourth root of 3 to the 4th is 3. And then I have 2 a's, that's going to become a squared. I've got 1, 2, 3 b's, that's going to be b cubed. And then the fourth root of b squared c. All right, last one. Let's see. Fifth root, that means I need to look at powers of 5. Well, we know from above that 2 to the 4th was 16, and I know that 32 is 16 times 2. So that means that 2 to the 5th, which is 2 times 2 times 2 times 2 times 2, is 32. This is a good one to know by heart. So if I've got the fifth root of 32, I'm going to write that as 2 to the 5th. A to the 5th, A to the 5th, and B to the 5th, B squared. There's 7 B's in total. I have perfect fifth, perfect fifth, perfect fifth, perfect fifth. And so this 2 is going to pop out. I've got 2 A's that are going to pop out. Not 2, like I'm going to write it as A times A or A squared. And then I have a B that's going to come out. And the only thing that's left over underneath there is that B squared. And we're done. Okay, so you get a chance to practice that. All right, let's see. The next thing is talking about adding and subtracting. So adding and subtracting in some ways is a little bit easier because I'm not going to give you stuff that's like super wacky. So adding and subtracting, you just have to remember to have like terms, and then you want to simplify your final answer if you can. So for this first one, I have a negative in front of this root. This means a negative 1. And so if I have negative 1 root 20 plus 2 root 20, that's just 1 root 20. And then I need to ask myself, is there a perfect square that's a factor of 20? And the answer is yes. And so my final answer here is going to be 2 root 5. You could simplify first and then combine, but I find it easier to combine first and then simplify. This next one, we've got negative 2 fifth root 64 minus 2 fifth root 64. We're just going to deal with the coefficients there. So negative 4 fifth root of 64. And then I want to be sure to double check, can I reduce the fifth root of 64? Well, we just said that 2 to the 5th was 32. And that means if I multiply that by 2, I'm going to get 64. So this is going to be 2 to the 5th times 2, which means negative 4 times 2 times the fifth root of 2, right? Because this one is a fifth that can come out. And so my final answer here, negative 8 fifth root 2. I have a couple more at the top for us to go over together. Okay, now for part C, I can't combine these together because they don't have the same root. So I want to see if I can simplify the square root of 54. I know that the square root of 54 is, well, I know it's 9 times 6. And so I've got a negative 2 root 6 minus 3 root 6 if I square root. And then now they have the same root. I can combine them together, negative 5 root 6. Same thing for part D. Let's see, we said that 2 to the 4 was 16. Is 16 going into 80 times 5? Oh, it is. So I can take this thing here, the 4th root of 80, and write it as 2 to the 4th times 5. It's kind of a hint that this is the 4th root of 5. 80 divisible by 5 is 16. Okay, so let's just simplify that. This is going to be 3 4th root of 5 plus 3. And then this 1/4 is going to come out. So it's going to be 2 times the 4th root of 5. And I'm going to bring everything else down. 3 times the 4th root of 5 plus 3 times. So this is 3 4th root 5 plus 6 4th root 5, which is 9 4th root 5. Okay, so the last thing, we actually have seen a couple of times already, the properties of roots. It's the same as they were for squares, and square roots. So the same thing applies for higher roots. So if I'm going to divide, I can combine together into a single root. using the quotient property of roots, which is right up here, I can either take a root that's already one fraction and break it apart, or vice versa. If they're separate, I can put them all together under one. And then the product property for roots says that if I have the same index, then I can go ahead and just multiply them together and put them under the same root. Okay, but so here's the main thing. They must have the same index. The index is that little number that's telling you which root you are. Okay, so for this first problem, I've got, if I just look at the number parts first, I've got a 1/3. And then I can take these two roots and I can write them as a single root. So 12x cubed over 6x. And now I can reduce this fraction. So 12 divided by 6, that's 2. And I've got x cubed on the top and x on the bottom. That's just x squared. And so now can I square root that? Well, the square root of 2 is just root 2. But the square root of x squared is x. That can come outside. And then there's still this 3 in the front. Right? This is really just over 1. And so here's my answer. Let's do another one. Okay, now the only thing that's different about this one is that I've already written it as a single root. And if we can, we want to try to simplify first. Okay, well, the only thing that I can do right now is I can simplify. I've got 40, I've got x to the 5th on the top, x squared on the bottom. That means x cubed in total, y to the 7, and then all over 81. Okay, now this is a square root, and I know that the square root of 81 is 9. And so lucky for us, we can split this apart. I can call this just 9 on the bottom. And then on the top, I need to break apart squares. So I know that 40 is 4 times 10, where 4 is a perfect square. X cubed I can write as x squared times x, and y to the 7, I'm going to write that as y to the 6 times y. And let me circle our perfect squares, 4, x squared, and y to the 6th, right? Because we can write that as y cubed squared. All right, so what's going to pop out of that root? This is still a fraction with 9 on the bottom. So the square root of 4 is 2, the square root of x squared is x, the square root of y to the 6th is y cubed, and then everything else that we didn't circle is going to remain under the root. And here is our final answer. Luckily, we didn't have to rationalize. So if I would have had a root in the bottom, I would want to rationalize. Okay, so the same ideas apply when you're dealing with multiplication. So for this first one, I've got, well, there's a 2 in the front. I'm just going to pull that out here. And then the 5th root. I know that I need to break this down into things that are perfect fifths. Well, 15 is just 3 times 5. And then x cubed, like none of those things are perfect fifths. And 81 isn't a perfect fifth either, but it is written as a fourth. It's 3 to the 4th. And x to the 5th is a perfect fifth. So what's great about this is that this 3 and these 4 3's make a perfect fifth. Okay, so let me go ahead and rewrite that. So I'm going to have 3 to the 5th times 5 times x cubed times x to the 5th. And then this perfect fifth and this perfect fifth are going to pop out. We'll have 2 times 3 times x. And then everything that didn't pop out of the root is going to stay there. And then lastly, we'll just multiply those together. So 6x times the 5th root of 5x cubed. This last one, you could try it on your own if you'd like, or we could do it together. Let's see. I'm looking for perfect cubes. Well, I know that 6 is a factor of 36, So I'm just going to leave 6 by itself. And then I've got x squared, y squared. Neither one of those are perfect cubes. And then I have 6 squared, and then I have x to the 4, which I can write as x cubed times x, and then times y. Okay, now I have a couple of things that I can combine together to make perfect cubes. I have the 6 and the 6 squared. I can write as 6 cubed. I have the x squared and this x, which I can bring down and call that x cubed. And I also have this y squared and this y to be y cubed. And then what's left? There's just that one more x cubed underneath the root. So now that these are all perfect cubes, the cube root of 6 cubed is 6. I've got 2 x's, that's going to give me x squared, and then y is going to be by itself. Okay, you're all set. I'll see you next time.